year 3 of our now 11-year journey as a lab. And Ankit is outstanding. Of course, he's brilliant. He's exceptionally creative. He has a drive and persistence that I think is inspiration to many of us. And he's been the key behind the success of many projects in the lab. Ones he's been directly involved in, and as well as those he's supported and mentored over the years in advancing everything from developing advanced robotics and manufacturing of commercial airplanes to mission planning support for Air Force fighter pilots. And as Ankit was working to finish up his master's degree, he did his master's focused on a project related to robotic manufacturing of commercial airplanes. As he was finishing up his master's degree in spring 2015, we began to discuss various PhD topics. And what I'll often do is give new master's students transitioning into the PhD the first choice to jump onto a set of new projects that happen to be starting up. And I had this strange project, which was applied, really working with people who in the Air Force and in other places developing intelligent decision support for mission planning for large force exercises in the Air Force. We have dozens of aircraft that deploy and conduct multi-day missions, and also very ill-formed. It wasn't exactly clear where the right AI support or cognitive support would be for that process, what existing techniques might be useful for it, and what techniques yet to be developed could form the basis of, say, a PhD project. And I pitched this project to the whole lab, and Ankit came forward and he said he wanted to jump onto that project for his PhD. And I thought to myself, this is a special person who is going to take an ill-formed project, but that there's clearly potential for, a lot of potential, but is also going to really need to work closely with real people who do real things and need to make real systems work. And he won't go deeply into it in his defense talk, but just wanted to give you some background on where the contributions that he'll present today sort of grew out of, and I believe are transformative for future intelligent machines that collaborate with people on both physical and cognitive tasks. Ankit is an outstanding mentor to many in the lab. He really enjoys sort of living in others' sort of technical problems. He's always interested in challenges. He's just so constructive by nature. He's just gifted in so many ways as a teacher, as a writer, as a mentor. It's really been a true pleasure to collaborate with him all these years, and his fingerprint is over everything our lab has done. And so, Ankit, I'm so excited for this great day and to enjoy your defense presentation. I'll pass it off to you.
Thank you very much, Julie. I will just share my screen and start in just about a second. A note to everyone that the meeting is being recorded, and I think as a co-host, Julie, if you could spotlight my camera, that would be perfect. Great. Thank you very much, everyone, for joining virtually and in person. I'm really excited to defend today. It's been a very long journey. And I'd like to talk to you about my research into Bayesian models for interactive robot training. Starting off right away, the autonomous systems and robots have a lot of promising applications and in a lot of domain areas, such as space exploration, disaster response, flexible manufacturing in high mix and low volume manufacturing, and flights to and from uncontrolled airports. These are domains where we would really like to deploy robots as they can take away the dangers for humans, but they are also extremely challenging to deploy automation in. While they're challenging for many reasons, some of the key reasons that got me interested in this work was it's very difficult to encode the knowledge of domain experts. There are experts who have spent years operating in these domains and have gained vast expertise. But when we try to formalize their knowledge, this ends up being an extremely difficult process. The second, these domains are such that the tasks need to be determined and developed on the fly, and it's very difficult to anticipate what a robot would have to perform in these domains beforehand. And because of that, it's also very difficult to formalize task objectives. And when we look at how we deploy automation today, we can see where this ends up being a problem. So because it is difficult to encode the knowledge of domain experts, Yes. So because it is difficult to encode the expertise of domain experts, and because we have this automation engineer who acts as an intermediary between the expert and in the deployment of the robot, uh, there is a very high chance of mistranslation of domain expertise. Uh, and because the automation engineer is one of the few ways in which we can actually modify the robot's behavior, a mistake baked into the robot ends up becoming harmful down the line when the robot is deployed. And secondly, as it is difficult to anticipate tasks a priori and difficult to codify these task objectives, you can see where this is headed. There is a very limited capability to modify the robot behavior once the robot has been deployed in the field. Uh, so the guiding principle and the vision from my research is that the domain experts must directly train the robot and not have the automation engineer as an intermediary every time the robot's behavior needs to be modified. Um, Based on that, we want the domain experts to directly train robots to interfaces and programming modalities which are intuitive to them. We would like the training to be data efficient so that the robot can learn new tasks with very few examples and very quickly. And lastly, we want the robot to allow for continual deployment, for continual improvement after deployment, so that in case there are any mistakes in the task specifications, that can be corrected on the fly and in the field. And there has been a lot of background research in ease of robot programming, and specifically my thesis contributes to and has drawn from three main areas of work. So the first is ease of programming robots, where the research has largely focused on developing new interaction modalities. So, for example, modalities which are intuitive to programming to domain experts, but not necessarily to people who have programming expertise and computational models for grounding examples such as demonstrations, language, and corrections into specifications that can be useful for the robot. The second area that I dropped on is planning and learning for non-Markov tasks. Non-Markov tasks are tasks which require the entire history of the execution to evaluate success. And these are really where the complexities for a lot of these are where really a lot of tasks in the domains are considered lie, where a simple reward is not easy to design, and we really have to consider these high complexity tasks. And the last part is probabilistic pedagogical reasoning, where prior research has developed inference algorithms for very complex distributions. We have developed a Bayesian view of learning, and we have developed cognitive models for pedagogy or for teaching. One of the things that was really interesting for me while working on this thesis was combining probabilistic pedagogical reasoning for non-Markov tasks. And this is not something that had been studied widely before. And this was something that was particularly challenging for me and very satisfying to work on. So I'll start by talking about some of the guiding principles. The very first is that the experts should interact with the robot only through natural modalities which are intuitive to them. And as examples, the ones that I've considered in my thesis so far are demonstrations of tasks and queries, where the robot performs the task and asks the domain expert whether something is acceptable or not. And the domain expert assessments then guide the robot's learning. We treat this as a problem where the expert has an intended task specification in mind pre-start, and the robot learns the specification by maintaining a belief over what the true specification is. And this is really the Bayesian view of learning, where learning is interpreted as sort of updates over probabilities or beliefs over what is the correct task specification. And then the last aspect is we are using task specifications that are modeled by formal logic, which enable for unambiguous semantics in what is an acceptable and what is an unacceptable task execution. So the primary contribution of my thesis is this framework of Bayesian interactive learning. And in the next few slides, I'd like to build up this framework conceptually and describe about some of the challenges and key results which we were able to demonstrate in the research for this thesis. As an example of the type of problems that motivate me, here's an example of a person who is telecommanding a robot and teaching it how to set a table. The table needs to be set in the configuration denoted to the right over here, where there are 5 objects and 2 of them are necessary, the dinner plate and the bowl. And note that the bowl is stacked on top of the dinner plate. What you're about to see next is a person telecommanding the robot from a web interface to and teaching it how to set a dinner table, for example. So here are the two executions which the person performs. In the first one, the person has placed the dinner plate, followed by the board. In the second one, the person has commanded the robot to place the dinner plate, followed by the fork, the knife, and then the board. Now, as a person who created this task, I know that the fork and knife are optional and the dinner plate is prohibited. But the robot has only seen these two task executions. So the questions that motivate my thesis are the following. First, what was the demonstrator's intent? If the robot has only seen these two task executions, what does the robot know about what the task is? The second question is, if the robot has only seen these two demonstrations, how should the robot go ahead and perform the task? And then the final question is, if the robot still has access to a domain expert, in this case, the teacher who taught it, who was telecommanding it, how can the robot best leverage the teacher's expertise going forward? Um, so, uh, so again, this is the framework, and I would like to talk briefly about how we are evaluating success. So the very first is the quality of the belief that has been inferred. And we first measured it by checking the similarity with respect to the ground truth specifications. And that tells us how close the robot got in its belief with what the correct task is. And then the second way of measuring the quality of the belief is the entropy of the distribution, which is a measure of the robot's confidence or certainty in what it has learned. The next way of evaluating success for these tasks is by looking at the quality of the task executions produced themselves. The very first thing that we want to check is the error rate, whether the robot is performing the task correctly, repeatedly or not. And then the second is flexibility, which is the robot able to perform all the correct ways of performing the task? And I'll show you some pretty interesting results along both of these lines as we go ahead. So the very first aspect of this work is specification inference, which is given passive observational data of an expert performing the task. Can the robot infer what the task is? As I said earlier, the expert has an intended task specification P star, and the robot always maintains a belief distribution PC. In the first part of my research, I developed algorithms that enable the robot to learn purely and passively from labeled task executions that are performed by the task expert. And something that was interesting was that this was one of the first Bayesian inductive inference for the demonstrator's intent as LTI specifications. So, as a demonstration, we taught the robot how to set a dinner table by providing it fairly unstructured demonstrations, which weren't segmented or they weren't performed in a particular order. We instructed the participants to set the dinner table in one of these four acceptable configurations. And apart from giving very basic instructions as to what the person must do in terms of handling one object at a time and not doing the task incorrectly, we didn't constrain the demonstrator in any way. And even with 30 demonstrations, we were able to learn at a specification that was 85% similar with respect to the ground truth specification. So the important thing to understand over here is there really isn't a benchmark for a Bayesian approach to specification inference before. And our system was among the first demonstrations for inductive inference of task specifications as an LTL formula. The next part of this thesis is planning with uncertain specifications. What the robot has learned is not a single formula that is correct, but really a belief over candidate formulas which might be true. So the natural question is, how do we plan with respect to a specification which by itself is uncertain? And towards that, we came up with algorithms that enable the policy computation under the uncertainty in specifications. And that involved answering what does it mean to satisfy a belief over what to do. We again were able to demonstrate this on the task of setting the dinner table. So we took the specification that was most uncertain with the table setting task, and we formulated it as per the punch formulation that we developed. when we solved for it, this is the four executions that were selected randomly. You can see that the robot sets the dinner table in many different ways. In fact, for this particular task, there are 6,072 unique ways of setting the dinner table which are acceptable. And in simulations, the robot had a very low error rate of less than 0.5%. But more impressively, using some of the evaluation metrics that we propose, the robot was able to uncover and perform 2,000 to 4,000 different ways of setting the table of the 6,000 correct ones of doing it. The last part is, as I said, if the robot has access to the expert, the robot can now learn iteratively, which is the procedure that has just input becomes the prior for the next learning iteration. And here the robot can learn either from demonstrations provided by the expert, new demonstrations provided by the expert, or from the expert assessments of what the robot performs. And here we develop active learning algorithms that do both. First, decide how to learn, what modality to use to learn. And then the second, if the robot is allowed to ask questions, what is the best question for the robot to ask? What is the most informative question for the robot to ask? And with a model, here you're going to see the two demonstrations that were provided earlier, but the difference is we were now allowing the robot to ask questions. So as you see in the first demonstration, the robot placed the dinner plate and the bowl. In the next one, it's going to place the dinner plate, the fork, the knife, followed by the bowl. But now that the robot is allowed to ask the questions, let's look at what questions the robot asks. In the first question, the robot actually flips the order of the bowl and the dinner plate. You can see over here. The robot will complete this incorrect task execution and ask the expert whether what it did was correct or not, and it wasn't. In the second one, the robot's not going to make this mistake again. It places the dinner plate, the fork, the bowl, and it has never seen the small plate being placed. So the robot is confirming whether this is optional or mandatory, and it's prohibited. This was wrong. In the very last execution, the robot's not going to place the bowl and ask the expert if the bowl was it mandatory or optional, and the bowl is mandatory. So this again was an unacceptable task execution. So when we actually refine the belief in this way and compute the policy rollouts, what you're going to see next is 3 task executions which were just performed by the robot, and you can see all 3 of them are different. So in the very first one, it just placed the dinner plate and the bowl. In the second one, it placed the fork but not the knife. And in the third one, it placed all the optional objects. And this is something that was learned only from 5 specifications. 5 task executions. So let's begin by describing the various components in this research. The very first is the question of task representation. I've talked about what P star and P are notionally, that they are the true specification and the belief over what the true specification is. But more concretely, these are formulas in linear temporal logic. So linear temporal logic is a branch of modal logic that provides a very flexible grammar to express temporal specifications. And these are the type of non-Markov specifications that I was interested in when I started this research. Some advantages of using LTLR is that it is a very well studied expressivity along with other frameworks of expressing non-Markov specifications like meta and branching tree logics. And we know the tasks that are expressible in it and the ones that aren't. So we know exactly the kind of tasks that are learnable when we use a formulation such as LTL. And the second aspect is that linear temporal logic itself is very popular in applications such as synthesis, which is correct by construction controllers, reinforcement learning as a reward through rewards, and symbolic planning, which is planning with Boolean predicates or just a symbolic notion. And I'll briefly go over how to describe LTL formulas. So in LTL formulas, the propositions are Boolean time series, which are defined through the recursive grammar that is shown here. And in addition to the usual propositional logic operators, which you might be familiar with, which are negation and conjunction and or disjunction, there are 2 temporal operators which might be new to some of you, which is next and until. In addition to these, there are complex operators or like non-shorthand operators such as eventually and globally, which can be composed of which can be composed through compositions of X and U. And I'll very quickly talk about what the satisfaction semantics for LTL are. So on the left, you see the satisfaction semantics for eventually A, which states that a property A must become true eventually and at least once between now and the end of task. So in the example above, you see that A becomes true at time step 4, whereas in the non-satisfying example, we see that A never becomes true. In the second one, we see globally, which means that A must always hold. And we see that in the first, because it holds from 0 to 10, um, there A has always held. Whereas in the second example, A becomes false at time equals 4, and that's why it's not something that satisfies the formula globally A. A very quick caveat, LTL is usually interpreted over infinite traces, but here we approximate it over finite traces by stating that propositions at the end time are true, are like they are unchanged after the end of the task. And there is another form of linear temporal logic called LTLF, which explicitly works with finite traces. And our framework is compatible with it, but as developed, it works only with the traditional interpretation of LTL. Finally, I talk about the operator until, which can be used to define orderings. So the property A until B implies that the property A must be satisfied till B is first satisfied, and after that it is unconstrained. So as you can see that this property is satisfied in the first example, but not in the second example. So let's look at how expressing specifications in LTL is. And here's the example of the table splitting task in a slightly different configuration. So remember that there are 8 objects: the dinner plate, small plate, bowl, fork, knife, spoon, mug, and glass. They are supposed to be set in a configuration which is shown on the right of the slide here. And note that the bowl is prohibited, whereas the spoon is optional. So let's see how we can go about writing this in linear temporal logic. So first is the specification that says never place the bowl. This is the negation operator. And what I'm saying is for the set of bowl, never place the bowl. So this was pretty straightforward. The next part is place all the necessary objects eventually, which is eventually place the dinner plate, the small plate, fork, knife, glass, and bowl. And we represent that by saying eventually F omega, where omega is the set of propositions that represents placing the dinner plate, small plate, and the other objects. And note that they are composed through this conjunction operator and. So to satisfy this specification, all of these objects or all of the individual subformulas have to be satisfied. Finally, let's look at ordering. Note that the small plate is placed on top of the dinner plate, which means that the dinner plate has to be placed first. In general, an ordering over subtasks can be represented through a directed acyclic graph or a graph that doesn't have cycles in the allowed paths. A sibling node must be executed, can be executed in any order, whereas a parent node must strictly precede the children and all the descendants. So in the example on the left, 2 and 3 can be executed in any order, whereas 2 and 3 must necessarily happen after 1 has been finished, and 4 must necessarily happen after 1, 2, and 3 have been finished. A good thing about directed acyclic graphs is that we can convert them into binary precedence constraints. So on the example in the left, this reduces to 1 must happen before 2, 1 must happen before 3, 1 must happen before 4, 2 must happen before 4, and 3 must happen before 4. And there are algorithms which can convert the directed acyclic graphs into a set of acceptable binary orders. Once we have the set of binary orders, we can represent them by saying that never do the antecedent until the precedent has been satisfied. And in this case, what we are saying is don't place the small plate until the dinner plate has been placed. So we can put it all together using conjunctions again. So what this is saying is that the property of never placing the bowl, the property of eventually placing all the objects which are required, and the ordering constraints all must be honored for the specification to be satisfied. And another lesson is that simple ideal formulas can be composed through these logical operators to create more and more complex task specifications. And even with these three simple templates of don't do something, eventually complete something, and the relative ordering for the subtask, you can see that we can define a very large number of specifications. So the first part of the thesis was how to learn these specifications from demonstrations using a Bayesian approach. And there were some challenges. So the first is that the expressibility of LTL, which we leverage to express complex task specifications, also becomes a curse because the hypothesis space is very large over what the candidate LTL specification is. And then the second is the I'm sorry. The first is that the uncertainty over multiple task executions that satisfy multiple formulas, we can't really break ties just from observational data. And then the second is the complexity in terms of the hypothesis space. Um, we resolve that using two of these approaches. So first is Bayesian concept learning, where we are maintaining a belief over candidate formulas and not necessarily constraining ourselves to finding out the correct formula. We almost let go of the notion that there is a single correct answer and that we can only ever know a belief over what the correct answer is. And then the second aspect, the intractable hypothesis space, was resolved by using a specialized grammar constructed using templates of smaller specifications which have been identified to be useful and have been used repeatedly. So the setting looks something like this. We have a data set of observations B, which is a set of sequences represented by alpha I. Following a Bayesian approach, the learner maintains a belief PC, which is all the formulas that conform to the template which I had shown earlier of the global satisfaction, eventual completion, and the orderings. And we can put this together through a Bayesian inference algorithm and obtain an updated belief, which is conditioned on the observations that were seen by the robot. So the first aspect of this is identifying that for a template-based approach, inference is equivalent to identifying the correct subsets of constraints, which need to be included in the final formula. Uh, to define priors over this, we use probabilistic programs, and specifically, I use a web-based probabilistic programming language called WebPeople, which has been partly developed here at MIT with the Computational Cognitive Science and the Probabilistic Modeling Group. And in a brief introduction to probabilistic programs, these are programs with stochastic choices and deterministic computations weaved together, and they allow us to provide very complex uh, inductive biases um, uh, to favor some or the other outcomes. So, as an example, this is a probabilistic program for creating one of those directed acyclic tasks. And as you can see, we are making probabilistic choices and then inserting them into the graph using deterministic computations. And this is just one of the probabilistic programs that was used in a framework. The second aspect is the likelihood function, and this I believe was the key for the successful demonstration that we had in our report. We used or we came up with a domain independent approximation to the likelihood function, which is based on the size principle proposed by Josh Tenenbaum in his PhD thesis. And what the size principle states that if we have two competing hypotheses which all model the observed data, the likelihood should favor the hypothesis which is more complex. Um, as and as an example, let's consider these two formulas. The first one is saying that never place the fork, eventually place the bowl, and do not place the bowl until the plate has been fixed. Um, and the second formula is, the second formula states that avoid placing the fork and necessarily place the dinner plate. Note that if we satisfy the second formula, we are not necessarily satisfying the first formula, but if we satisfy the first formula, we will always satisfy the second formula. And think about what this means when you're observing someone setting the table. if you see someone setting the table repeatedly who satisfies the first formula over and over and over again, the more such examples you see, the more confident you are that the first formula is the correct formula and not the second one. This, despite the fact that every single observation that you've seen has actually satisfied the second formula. And what was really key in Tenenbaum's thesis was that this size principle is very important for inductive learning. And the traditional view was something that wasn't dependent on this complexity, where the likelihood odds for all hypotheses which model the observed data were equal. And this bias of favoring the complex hypothesis was something that really enabled models to learn inductively or purely from positive examples. And we see that in the example of setting the table right there as well. If we consider the similarity, note that higher is better and the maximum value is 1, where the inferred specification is exactly equal to the true specification. Note that it starts off low, and as we see more and more examples, it approaches convergence to the true specification. Whereas if we look at the CI, which was the traditional view, which did not adhere to the size principle, um, seeing additional data really made no sense to the belief, or seeing made no advantage or disadvantage to the belief of the learner. It always favored the hypothesis, which modeled all the formula with the highest probability. And similarly, we look at the entropy, which is the measure of the confidence of the distribution of the model, and note that lower entropy is higher confidence. We see that seeing additional data points does not improve the confidence of the model at all. Whereas with the CB, with the likelihood that the CB likelihood function models the size principle, we see that the confidence of the model increases as it sees more and more data. And this was just one example. We actually saw this across many ground truth specifications in simulated trials. So this is the statistics with the median and the interquartile range for 500 trials with very different ground truth specifications. And in almost all of them, we see the similarity increase as more data points were observed, and the entropy decrease as more data points were observed. So in the original work, we had demonstrated this on our simulated domain and on the task of inferring how to set the dinner table. But we also applied this to many different domains in collaboration with different researchers. So in the very first one, we applied our models to inferring the mission objectives for large force multi-aircraft combat exercises, which were the scenarios were generated in simulation. And we saw that the LTL specifications that our model learned, the evaluations that they generated matched with a very high level to the experts' evaluations of the scenarios, up to more than 95% match. And in the second work, which is with one of my former lab mates, Joseph Kim, we applied a similar Bayesian approach to inferring LTL specifications for generating contrasted explanations. So if we had a set of plans uh, which were acceptable and a set of negative plans or unacceptable plans, we were able to infer a minimal explanation that separated these two or that explained why they differed. And we applied that to a wide range of symbolic planning domains from the international planning competition. Well, I won't be going into too much detail in these two works here. I'll be very happy to talk about it offline or in the question and answers. So that concludes the discussion of Bayesian specification inference, which was a model for performing inductive inference of the demonstrator's intent for non-Markov task specifications. So the next problem that we look at is planning with uncertain specifications, where the robot must generate a policy to perform the task when it only knows the belief over what the true specification is. And there are two key challenges here. The first, what does it mean to satisfy a belief over limit until logic formulas? And the second is, given a belief P3, uh, how do we compute formulas that satisfy that? So to answer the first question, there really isn't a single answer to this, and it involves a trade-off between creativity or flexibility in task execution. In the case of setting a table, the different orders that could be taken, and risk aversion, which is trying to adhere to the specification as best as possible, and not making a mistake. Um, and we propose four evaluation criteria that model what it means to satisfy a belief. And in today's talk, I'll be covering two of them. So the first one is the minimum regret formulation. Note that this is a summation over all the formulas that lie in the support, or all the formulas which have a non-zero probability as per the belief theory, uh, and the satisfaction check of whether a task execution of sequence alpha satisfies the formula or not. And note that this is weighed by the probability of inclusion. So this is really the expected value of whether a particular task execution satisfies the ground truth formula or not, as per all the hypotheses in the model's support. And what this means is that this is the belief of the model that a given task execution is correct. So when we maximize the minimum regret criterion, what we're maximizing is the probability that the model would label this execution as acceptable. And what we see here is a chance constrained version of this, where we select a subset of the entire support C delta, which has a cumulative probability mass of less than delta. But delta is the maximum acceptable error probability set by the user. And here, the learner becomes agnostic to task executions that do not satisfy that do not satisfy this small part of the task specifications. So moving on. Next was the question of, we know what it means to satisfy the belief over probability functions, but given a distribution TP, how do we actually satisfy, or how do we compute the policy that satisfies this belief? And the answer to that is to compile the non-Markov rewards represented by TP into a reward machine, which can be used as a Markov representation of the task. Reward machines were a fairly new formalism for representing non-Markov tasks, which was proposed by Toro Ekata, Alberto Camacho, and the group at UOFE. And they have some excellent analysis of what the expressivity of this is with respect to different formal specification definition languages. But let's look at an example over here to ground it more concretely. Here's our familiar formula. Do not place the fork, place the bowl, and place the bowl after the plate. We can convert this into a Bushi automaton or a reward machine, which is represented over here. This tracks the progression of the formula, which is at any point what logical formula must be satisfied from that point forward for the whole task to be satisfied. So we start off in this state, which is the original formula. Here, if we place the fork or we place the bowl before the dinner plate, we fail the task because we have not correctly completed it. Which represents which represents this transition. If we place the fork, if we do not place the fork and the bowl, but we place the plate, we end up in this state where from that point onwards, we just need to place the bowl to complete the task. Again, over here, if we place the fork, we go on and fail the task. But if we place the bowl and not the fork, we complete the task, which is represented by this state. So what we have here is a Markov representation that has the sufficient history to evaluate whether the task execution was correct or not. And we can now compose this with the transition function, or with the environment function. And what we get is an MVP, which can be solved by a lot of techniques in prior research, a lot of planning algorithms for reinforcement learning and planning with Markov decision processes. But this was when we had a single formula which was confidently known. What if we have a belief over formulas? So let's consider the second formula, which tells us to avoid placing the fork and only place the plate. And let's also add the probabilities over here, where the first is 0.3 and the belief that the second formula is correct is 0.7. We can naively take a cross product of these two automata to get an automata with 12 states, where we pick one state from the first automaton and one from the other, and then plan with respect to those. But note something interesting, which is if we consider these two states where the first formula is satisfied and the second formula is not, these cannot exist together simultaneously. And there are many such redundant states. So if we perform a breadth first enumeration of the states which can be reached, which are feasible, we actually get only 5 states instead of the 12 that we were getting earlier. And when we have multiple specifications, the reduction that we can get with doing this breadth first enumeration and eliminating all the unnecessary formula is actually really large. So in this example, the minimal automaton only has 5 states. And here are the states where both the formulas, the truth values of both the formulas are determined. They are either satisfied or dissatisfied. And these are really the reward generating states of the reward machine. If we apply the minimum regret criterion over here, these are the specific values of the reward in each of these states, and the rewards in all of the others are 0. Um, and finally, when we take a cross product of that or the concatenation of that with the environment automaton, we obtain M spec, which is an MVP. And this is now compatible with any of the favorite deep reinforcement learning or reinforcement learning algorithms. Note that this is only providing a way to compile the rewards into something which is expressible. But what it doesn't do is actually reduce the hardness of the problem itself. Some of the challenges for reinforcement learning are the sparse rewards of processes like this, which only occur after many time steps. And while this doesn't mitigate that, it at least allows for a sound representation of the task in terms of the reward machine. So let's talk about some of the quantitative results of the table setting demonstration that we saw earlier. So note that in the posterior distribution from 30 demonstrations, we had 25 unique formulas. The formula with the third highest probability was the actual ground truth, which meant that the formula that the model believed to be correct was actually not the right formula. So if we had only planned with respect to the most likely formula, we would have had a very high error rate of 50%. Note that the reward machine would have been quite small, so the computation overhead would have been low, but this would have resulted in a very high failure rate. However, if we use our Punch formulation and plan with respect to all the formulas in this, all 25 formulas, we get a large reward machine of 3025 states, which had a very low error rate of 0.015%. But note that it was able to uncover about 2000, so 1962 valid orders out of 6072 actual valid orders. But more interestingly, let's look at the chance constraint case where we set the failure probability threshold to 0.1 and 0.3%. And that resulted in only considering probability mass of 4 or 3 formulas respectively. And note that the reward machines here are much smaller than the full distribution, but just a little bit bigger than considering just a single formula. And with this, we were able to uncover many more valid orders or valid ways of doing the task without a significant increase in the error rate. And another side effect of using non-Markov specifications is our model is now more robust to some types of task disturbances. So in this case, I've hidden the small plate from being visible to the robot. And here the robot will not be able to locate and pick up the small plate. But the robot knows what the correct task specification is or a belief over that. And the robot will not proceed or complete the task till it's finished. So here the robot's waiting for me to review the dinner plate, which I do now. And now the robot will continue the task and complete placing the dinner plate and the bowl, which was a subtask that was actually dependent on the small plate being placed. So that concludes the discussion of planning with uncertain specifications. Right. So the next part is refinement of task specifications. So this leads to the third question of what if the robot had access to a domain expert and was able to get additional demonstrations or query assessments from the robot. And the key challenge over here was how to estimate the value of anticipated information. So I'll just briefly give a description of what the setting here is. So here the teacher can provide demonstrations or acceptability assessment at any iteration. For each iteration, we are using an iterative Bayesian inference model, where the posterior belief of the prior iteration becomes the prior for the next iteration. Next, the robot operates in two modes, refinement and deployment. In the refinement mode, the robot can ask for new demonstrations or assessments from the expert, and by actually deciding which modality to seek next, like whether should it ask the demonstrator to perform a task execution, or should it perform a task execution and ask the demonstrator to correct it. And in the deployment mode, it takes the final belief that was generated and uses the transformulation that we just discussed to compute the policy for completing the task execution. Uh, a key assumption that we make in the following discussion is that the teacher will always have access to the robot's belief and the update model. And this is important as I'll come across it in a bit. So let's return to the reward machine that we were talking about earlier, where the robot is simultaneously trying to plan between P1 and P2, and satisfying P1 automatically satisfies P2. So here, if the robot wanted to ask the question of what is an acceptable task distribution, note that any execution that ends in these two states, where both states are either satisfied or both states are dissatisfied, is not very informative because the robot doesn't really learn anything from getting a label over here. However, if the robot performs a task execution that ends in the state labeled on the slide, here the second specification is satisfied, but the first one is not. And any label over here, whether acceptable or unacceptable, is informative for the robot. So from the learner's perspective, a task execution that ends in this state is most informative. Now, from the teacher's perspective, the teacher has the advantage of two things. One, the teacher knows what the ground truth specification is. And let's assume in this case, it is the second formula. And the teacher also knows what the robot's current belief is and what the belief update model of the robot is. So if the teacher knew that, uh, and the teacher were to provide a demonstration that ends in either of these two states is acceptable. But a demonstration that ends in this state does not resolve the learner's ambiguity. And which is why a good teacher, an optimal teacher, would not actually perform a demonstration that ends in this state because that doesn't resolve the ambiguity for the learner. A good teacher, in fact, would provide a discriminative example and or what we call a pedagogical example. Now, note that not all teachers or not all human teachers are optimal, but we do see evidence of this pedagogical thinking when we ask someone to teach. Um, the and in the prior literature, people have been modeled as noisily optimal demonstrators, where they do the right thing, but not always, and it's controlled by a distribution which has a parameter gamma. So a low value of gamma, which can even go to negative values, means that the teacher is not being pedagogical or being anchored to some of the earlier task executions that they have shown. And a high value of gamma, extending up to infinity, uh, makes the teacher's distribution over the optimal task execution more and more sharp. So at infinity, the teacher will always select the correct task execution to perform. While at zero, the teacher performs any acceptable task execution at random. And for negative values, the teacher sticks to certain types of task execution, or we call that anchored. So to formalize this, what we are trying to do is to estimate the value of information that's going to come to the robot. And there are two choices that need to be made. We call them active learning and meta choice. So formally, if the learner has to perform a query, the learner must estimate what's the value of showing a particular task execution and what is the expectation over all possible acceptability labels provided by the teacher. Uh, and here the learner has control over what is the actual data point which needs to be labeled. Uh, and if the teacher is performing the demonstration, the learner must estimate the teacher's pedagogical selectivity and it must compute this expectation over all possible trajectories and candidate specifications with respect to which the teacher must demonstrate the task. So, in an active learning scenario where the learner gets to choose the next data point, the left value is what it estimates. And while deciding which modality to learn from next, whether to ask the teacher for a demonstration or to ask a query, the learner estimates both these quantities and goes with a one which is greater. So we have three candidates for what the information utility functions are, and these are derived from literature in active learning, which has very actively considered the question of estimating where the model should learn from next. And the three candidate functions that we were able to be operationalized in reward machines context were uncertainty sampling, information gain or entropy reduction, and the notion of model change, which is how different is the new or the updated belief from the prior belief. So here are some of the results that we got in simulation experiments. So recall with the table setting task of how we were able to get the robot to ask informative queries, but that was just one ground truth formula and one domain. Here in simulation, we compared or we conducted experiments where we repeatedly kept on sampling different ground truth formulas and allowing a simulated teacher to either demonstrate or assess a simulated learner's queries. So in the first task, we consider a case where the robot was only learning from questions or only learning from queries. And what we see here is that the three information utility functions that we consider, uncertainty sampling, information gain, and model change, have a very similar trajectory to improvement of its similarity with respect to the ground truth formula. Note that in all the cases, more than 50% of the executions, we were able to learn the correct specification, and we were able to get more than 75% similarity for 75% of the trials. So what we are seeing over here is the interquartile range. Next, when we allow for meta choice, which is when we allow the robot to choose what the next what information source the next iteration is going to come from, this performance gap widens because each of these information gain functions favors either the demonstration or asking questions. And this was the case with the non-pedagogical teacher. And we saw that the median for the uncertainty sampling information function was the highest, and it was lower for information gain and model change. Next up, we conducted performance experiments for the impact of the teacher's pedagogicity. And here we were only allowing for teachers' demonstrations. So here what we see that learning purely from demonstrations is very strongly dependent on how pedagogically selective the teacher is or how good the teacher is at teaching. When the teacher is optimal, we see that the learner learns very quickly, gaining more than 95% similarity with just 5 task executions seen. But when the teacher is anchored to some of the initial demonstrations that we have shown, we see that the learner does not even converge to the right specification for more than 75% of the demonstrations, which is the lightest line over here. So the good news is when we actually allow the learner to assert a meta choice, we can overcome this limitation even for the most non-pedagogical teachers that we simulated. And that is shown in the median values over here. And the other thing is, as I said, the utility functions have an impact on the relative performance when the meta choice is asserted. But here it flips. So in a pedagogical teacher, information gain and uncertainty sampling actually trusted the teacher more and asked for more demonstrations early on. And that leads to a steeper learning curve early on as compared to uncertainty sampling. So really the design recommendation over here is when we are deploying learning from demonstration systems, we must understand that the teacher's pedagogicity matters. For a highly pedagogical teacher, using model change or information gain as the information utility function for meta choice makes a lot of sense because they actually do leverage or they do trust a pedagogical teacher more. But when we are seeing a teacher who is not particularly pedagogical, uncertainty sampling seems to be in favor. And finally, that's the conclusion of it. So finally, this was our work on interactive robot training for refinement of the task execution. And what we presented were active learning algorithms for asserting both a meta choice and for selecting the task execution to learn from next. So In conclusion, we presented this Bayesian framework for teaching tasks to a robot interactively. And what we first demonstrated was an inductive intent inference for multiple domains, adopting a Bayesian view. Next, we were able to formalize the problem of planning with uncertain specifications, where we allowed the robot to learn task policies when the beliefs were only known, where the specifications were only known as a belief. And finally, we were able to come up with active learning algorithms for refining the belief that best leverage the expertise of the teacher who was teaching the task to the robot. Some of the future directions that I'm very much interested in is actually deeply consider the question of how does teaching differ from performing the task. In the user studies that we performed, we repeatedly saw that people were much better at teaching a robot how to perform a task than was expected by our worst case pedagogical models. And this involves the notions of coverage of task educations of the curriculum by which someone is teaching the robot. It also considers the question of at each point, what is it that the teacher would like to assess from the learner, and what is the teacher's mental model of the learner's really separate. And while we consider that the teacher knew all of these questions, in practice that is not something which can be taken as an assumption always. Next up, I'm very interested in the appropriate abstraction for representing the hypothesis space of tasks P. It's very important that the tasks that are learnable by the robot are a superset of the tasks that the expert actually wants to teach the robot. And if and when there is a mismatch between what the teacher wants to teach and what the robot can learn, the robot should be capable of communicating its capabilities and limitations very explicitly. And there is some recent work on doing that in machine learning domains and Markov domains, but not so much in the sense of non-Markov tasks that are very interesting to me. And finally, I'm interested in better information seeking strategies. What I'd implemented here was a binary acceptable or unacceptable query. But there can be much more information packed into an active query that is performed by the robot. So query framing for maximum information gain and how to intelligently frame these queries is something that I'm very interested in. And this is something that I would really be interested in pursuing in the future. So none of this would have been possible without my excellent collaborators, Pritish, Sen, Samir, Joe, advisor Julie, and my collaborators at Dr. Martin, Kevin, Patrick, and Kevin Odin. And with that, I'd like to conclude this presentation with a summary of the contribution side, and I'm open for any questions that the committee and the audience could have. Thank you very much. Julie, could you please spotlight the defense committee?
Yes, let me work on that. Ankit, thank you for that excellent presentation. What we'll do now is move to the Q&A session, and we'll start with our committee members and then our readers. And then the faculty member that's not an alumni of our lab. So let's go in the following order. Let's go Hadass, George, Nick, Vaibhav, Steffi, and then Michael, if you have any questions as well. I'll put that order into the chat. And so Hadass, do you want to kick us off with the first question?
Sure. So Ankit, that was a great presentation, and this is a really wonderful thesis. So well done. So I have a few questions, not so much about the details, because I've asked a lot of questions about the details in the past. Kind of more about the kind of bigger picture, future directions aspect of it. So you talked a lot about LTL, and your thesis is around LTL, which is a discrete logic over propositions. So you need to somehow define what those propositions are, right? So the abstraction is baked in. And there are no notion of continuous aspects, which are very important for robotics. So a few things, kind of what are your thoughts in terms of maybe different logics, maybe different representation? Is LTL the right representation? Where do you sit in that space?
Absolutely. So I do not think LTL by itself as it stands is the right representation for everything because LTL as defined does not allow us to go below the symbols. But there are extensions of LTL that allow uh, for continuous predicates, or you can almost think of them as parameterized predicates such as signal temporal logic. So my very next step in thinking about it is to leverage the temporal operators of LTL for the temporal compositions, but then use other ways of learning the parameters for STL predicates themselves and frame them as learnable functions. I haven't had much work or like I haven't had concrete research in this direction yet, but that is one of my future directions. I also don't think that logics by themselves will be adequate because they do not have a notion of optimality, only of satisficing or only of satisfaction, not even satisficing. So maybe coming up with a common specification language that can unite optimality and satisfaction together is something that would be very desirable. But as I said, I don't have answers to that right now, but these would be the questions that I would consider.
Yeah, well, STL first of all has the temporal operators, right? So you wouldn't need LTL, but it also has the notion of robustness, right? So you do have continuous metric, so that might be. But I think so. STL seems like a good.
Right. So when I talked about optimality, I meant something like I don't think we can specify optimizing fuel consumption while satisfying an STL formula, but maybe that could be done as a robustness metric. And like I haven't dabbled with STL much, but like I would like to hear your thoughts in future on that.
Yeah. I think what would be interesting for me to kind of learn from you, not right now, but in the future, is how much of the kind of belief representation over how does it scale? Because I can see how I can see kind of technically that it would work. You would have a much larger parameter space because it won't be just discrete. But then the question is, what breaks, right? What are the things that cannot happen? So I think that's really cool. The other thing I wanted to ask is something actually what you mentioned with the future work, the mismatch between robot capabilities and maybe expectations, demonstrations, the tasks that you have in mind. So have you seen any examples of that in all the kind of user studies that you ran, or is it something that you're hypothesizing in the future? Where is that? I mean, I think it's a really fascinating question. I'm just wondering if you have some concrete examples.
So in the study, no, but in the discussion with the lab mates, reactor specifications came up very frequently, which is, can I program the robot to do something when I say jump in front of it?
Can you repeat the last sentence? It's very echoey, the room you're in.
Oh, I'm sorry. So reactor specifications where a stimulus elicits a certain response from the robot was not something that was in the hypothesis space. We had conversations of can the robot try to learn the cause and effect model of that. So that is a clear example of like a mismatch in expectation and capability, and something that we don't have an answer to right now. So that was one of the examples of just within LTL where expressivity wasn't enough. And then the second one was the sub-symbolic learning of can I teach the robot to place the spoon at a different location? And that is not something that we can support right now. And we don't really have a way of communicating this to the expert of what the robot can learn and what the robot can't learn. In terms of works which have addressed this, I'd like to call out some of my work with Serena and Yudun on explaining classifiers by examples. But this is pretty far removed from robotics as of now. But the idea was that if we have a pre-trained classifier and a model of the potential data points that it can see, can we query the classifier to give us examples of one class versus other class confidently, or examples of images where it would actually get confused between classes? And I know that Serena and Milun, along with Nadia, have gone on to extend that to some robotics applications as well for analyzing motion planners called Crocus. But I would be very interested in trying to see that sort of an approach applied to reward machines and non-markup tasks.
So let me actually follow up with one thing. You talked about reactivity. Is there anything preventing you from using like GR1 or reactive versions of LTL where some of the propositions are controlled and some are uncontrolled? Doesn't seem to me like there's anything preventing you from doing that. Maybe not the planning. I don't know about the planning. Definitely the learning.
I'm sorry, could you just repeat the last question, last couple of sentences?
Yeah, I don't know how it would translate to the MDP formulation or to the PUNS work that you did, but for learning reactive specifications, is there anything preventing your current framework from doing that? Granted, you would have to say these are symbols that are environment symbols, these are robot symbols, but is there something fundamental that won't work?
So my intuition on this is what you said, which is I don't see what prevents it, but I do not have empirical evidence to say that it works. One of the things that I am concerned with is spurious correlations because it will pick. I'm not sure if it will pick up on what is the proximal cause of the reaction or was it a spurious cause. And then the second aspect of this is I'm not sure it can be done purely from observational data, but I think that there is a pretty good, there's a very good research direction of using the refinement or active learning methodologies to actually query for what is a cause and what is not a cause.
Yeah. I mean, I think the fact that you have some notion of generality versus, I mean, right now you're trying to find the most specific formula. Mm-hmm. And maybe you don't want to have the most specific formula in that case, because that would be spurious. But it feels like the mechanism should allow you to do that as well. All right, thank you.
Like I wouldn't try to say that it does it without having empirical evidence or at least a demonstration of doing that.
That's fair.
Thank you, Ross. Thank you. George, go for it.
Hi, Ankit, that was a great talk. Wonderful to see everything put together. We've also had lots of discussions about low-level details. And also Hadas already asked my first question, so I'll go to my second question. So one of the things that's always kind of felt interesting and maybe a bit neglected is you're treating your trajectories as sort of your demonstration trajectories as kind of positive examples only, right? Like you see what the person does. And sort of related to Hadas's first question about the sort of symbol level versus the low down level, you actually have those low down trajectories, right? And so and you have a distance metric where you can say, okay, well, this was the direct path from A to B. And so I wonder if we could use that information to infer implicit negative examples, like you avoided something on the way from A to B, right? Or some. Can you comment on if we can get richer stuff? I mean, we don't have to break the LTL formalism, but I wonder if there's extra information we could get out because we have that metric and that kind of shortest path planner.
There absolutely is extra information that we can capture over there. And I think in terms of simpler LTL tasks, I know of work from Professor Tenenbaum's lab, which talks about planning as inverse inference, inference as inverse planning, where they actually look at these deviations of the trajectories from what would be optimal. And I know that there is work from Professor Gagan's lab as well at Berkeley that explicitly considers these signals. The challenge for me was, is the additional computational complexity of LTL and the temporal operators too much to handle these together or not? So I haven't really had the time to see if both of these approaches can be integrated. But they both lie in a proper, they're both a Bayesian approach, which leads me to think that they can be integrated. But I don't think that there's work out there which explicitly does that.
Great. Yeah, I think that would be fun. And one of the other things I really like about everything you've done is, the kind of Bayes rule gives us this way to plug in all this information together and make everything work neatly. And I really like that you have that, you've managed to get to the point where you have these distributions over a formulae, which means that now we can include other stuff. So I was wondering if there's extra stuff that we could imagine including, like gestures or gaze or people frowning, or like what's the coolest, most fun, most out there thing we could imagine putting in Bayes rule?
Oh, absolutely. I think there's so I have only presented learning modalities that include demonstrations and queries. And as you said, there are just so many sources of information. Like one good recent work that I like is again from Professor Gansad in Berkeley, which talks about a unified model for all of these inputs, um, which they talk about as like ways of manipulating the belief distribution. They have restricted themselves in their current analysis to linear Markov rewards, and like in theory, there should be nothing preventing us from applying it to non-Markov rewards as well. But the correct computational rounding models.
Cool. Okay. And so the last question I have is kind of user interfacey. So you'll have to forgive me here because I'm a little over my skis. But I thought it was really interesting, that you were able to show that if a teacher kind of taught pedagogically, then the robot learns much faster. But then there's a bunch of assumptions we have to make about the teacher, like that that they know your belief distribution and all that other stuff. And so I was wondering, like, what's the minimal kind of most friendly user interface that we could build where, like how do we, is there a way where we can give the teacher some feedback? I know that sometimes when a student does something, they'll do it more slowly if they're not sure, or they'll kind of look at me while they're doing something and I'll look at them. And, I wonder if there's like a natural way where you could imagine visualizing like the tree of trajectories, and some of them are dark and some of them are light, and there's the kind of main line you're taking, and maybe, it would just be interesting to see if we could get a human in and see if we can guide them in teaching this way. Do you have any thoughts about how that might work?
Not concretely, because I think there are lots of like interconnected parts over here. Because I think so. One of them is just ways for the robots to be more expressive beyond the task. Like, how do you show uncertainty in execution? And then the second question is, what should the expert be observing? Like, what display should be available to the expert? And I think that specific answers to all of these require us to like commit to answers for all of these things, and which makes a study design quite challenging. I'm hoping that as we learn more about human-human pedagogy, for which there's significant human factors work already out there, and when we start looking at human-robot teaching models, we can start testing some of these human-human pedagogical theories for robotics as well. So there is just a very rich set of questions that I think need to be answered with user studies first before we can start making hypotheses for what would it look like for robots to actively leverage these pedagogical capabilities.
All right, those are all my questions for now. Just once again, wonderful work, and great to see this talk. Thank you.
Thank you, George. Nick?
All right, just to echo Hadas and George, I could really great work. Really nice to see it come together. It's one thing I was thinking about is, so it's a relatively complicated system to go from demonstration to inferred specification to execution, et cetera. And you made it work, which is great. But I think we all understand that it's not easy to get systems as complicated to work on real robots, and you have to be fairly expert in what you're doing. So what's the most brittle part of your system? What's the trickiest bit to get right? What's the bit that, like, if you came in as a rookie and tried to make it work, you would be scratching your head wondering why it didn't work? I'm sure there's a bunch of such things.
Yes. So I think robust, reliable object detection and motion planning was the biggest challenge for me, because I needed to be sure that when you're programming certain objectives, when the robot is trying to make certain motions, they have to be safe. They shouldn't collide with the person, and they need to be cognizant of the environment in a dense form. So whenever we are working with contact width or like very constrained spaces, this work will be challenging without good motion planning algorithms. So what allowed my demonstration on the dinner table to work was that once the robot got above the surface of the table, it was very unconstrained. But I think for me, that would be like the not low hanging fruit, but that would be the most proximal challenge for me. I think another challenge for me would be sparse rewards in RL algorithms. So all of these logical formulas ended up with sparse rewards. And I think like exploration heavy RL algorithms are an active area of research. So what like in an ideal world, for my system to work best in deployment, reliable object detection, fast motion planning, and um, and really like fault tolerant vision system would be very crucial to get it to work on a real robot. But an advantage of these questions are uh, sorry, an advantage of these problems is that they can be framed for a general purpose task where we have to define the endpoints of the robot and then some planning system has to fill in the gaps. But that doesn't need to rely on the ambiguity of the user's demonstrations necessarily. So I think I consider my research so far to tackle the ambiguity of the person's demonstrations and trying to understand the intent. But then parallel work along the lines of making systems robust to respond to specifications is very important.
Okay, that's really interesting. It certainly is. I mean, I think I've certainly fallen into the trap of thinking that the specification is the hard part, and motion planning is kind of like, you know, a solved problem to at least first order, unless you have a really complicated motion planning problem. And I think you're pointing to the fact that it's just not quite that simple, is it? That's great. And maybe I'll just ask one other question. The you touched on it, I think, at least part answer to George's question. But the Bayesian formulation assumes a prior. And a prior, I think, is where you're baking in an inductive bias over preferring some specifications over others. But you never actually said what the prior is. So A, what is the prior? And B, is that something that is of interest in further study? Because you could imagine putting sparse rewards as part of your prior. You could imagine putting safety as part of your prior. But I'm not quite sure how one goes about doing that. So if you have thoughts about, so A, what was the prior used? And if you have thoughts about making that richer, more expressive, I'd love to hear them.
Sure. So the prior that I used was quite flat in the sense of all possible subsets would have equal probability. So if I was using inclusion and exclusion as that, it was just 0.5 conflict. So any outcome would have an equal prior under that. In constructing the directed acyclic graphs, I was using iterative algorithms to construct the graphs, where the prior was that simpler graphs which have fewer connections have a higher probability, and the probability kind of tapers down as there are more and more dense interconnections. So these are described as probabilistic programs, and the details of probabilistic programs are there in the thesis document. If you'd like, I can share some of the slides which go through what the priors were in more detail. But we absolutely saw that there was an impact of the selected priors, either on learnability or on how many demonstrations were required to converge to the right examples.
Okay, cool. Thank you. I'll stop here in the interest of time.
Thank you, Nick. Vibha?
Thank you, Ankit. That was a really like comprehensive talk and a very exciting work. So I'll first start with a clarification question. So in your work, like you learned specifications, but what did you assume in terms of knowledge about the environment? Like, did you assume the transition function was known, symbols were known, and so forth?
Sure. So in the specification inference work, what I'd assumed was that the propositions that are important for constructing the specifications were known. But apart from that, I didn't make any assumptions on the transition dynamics of the system, which allowed or the action space that the agent was using. So that allowed the learned specifications to be, you can say them to be task-centric and not agent-centric. But in the punch formulation for the evaluations, I use planning algorithms and not reinforcement learning. So the environment transitions were known. But because I compiled it into an MVP, if the MBB planner or the RL planner is fast enough, in theory, it should be able to compute it quite quickly. But I wouldn't say that is an assumption that's always a given.
Got it. So in if I understand correctly, in the punch formulation, the knowledge of transition function becomes critical because you're using planning. Okay. So if let's say that,
Just to clarify, Punch doesn't require a planning-based formulation. It will compile it into an MVP, which can also be used by a reinforcement learning solver. For
okay.
all the results presented in the thesis, it was with a known transition function.
Okay. And when you would apply reinforcement learning, let's say in case transition function is unknown, do you anticipate like any challenges, or do you think it will be it's more of an implementation challenge versus like a technical challenge?
Yes, so I haven't directly worked with reinforcement learning algorithms, but the work that I would point you to would be there are quite a few, but I think the reward machine work would be a good place to start, where they explicitly develop a reinforcement learning based planner without the knowledge of the model to perform tasks with small reward machines of the size of about 100. And another thing that they've done, which was really cool, was they actually use value iteration within a reward machine to scaffold the rewards and make them less sparse. Like it was still not a dense reward, but it was denser than just satisfying the final specification. So there is some empirical evidence that we can scaffold LTI rewards using the reward machine structure. But the sparse rewards, as always, are a problem for reinforcement learning algorithms.
Okay, thank you for that. And I think like one more very interesting connection could be like in the Punch formulation, you have multiple fees or like a probability space over fees. So they could sort of serve as a curriculum. So the first fee could be the first one. Yeah, that's very exciting. The other sort of question that I had was, which was sort of closely related to your third one, is when I work with robots or when we teach something to robots, a lot of times our intent, what we want to teach, changes based on how the robot does a task. So let's say if the motion planner gives something widely different than what we expect, then we'll add some more constraints and so on. So like, how would your framework extend to the case where the fee that the human carries, the expert carries, is actually dynamic, like it changes over time? The changes won't be like substantial, but maybe like minor tweaks.
So I think the answer to that is it's a bit complicated. So because we're using an approximation framework, the probability never quite goes to zero. But we are also using a sampling-based framework which constructs a procedure according to sample. So if that drops off the sampling list, the probability will go to zero, and then that's a case of catastrophic forgetting. But I would say that that's why I say that the current framework is not capable of handling dynamic or variable specifications. To do that, what we would require is a prior that allows for some sort of reset to relearn the specification. But I don't think that there is explicitly a way of preventing catastrophic forgetting. There could be a way of like allowing it to relearn something, but not enforce that it doesn't forget what it has done.
Got it. Thank you again. That's all my questions.
Thank you, brother.
Wonderful. Thank you, Vaibhav. Steffi?
Hey. So my first question is about what happens when you try to do this in partially observed environments where you don't necessarily get to see all the objects in advance, and you might have to go find them, figure out where they are, and then once you know where they are, move them around or make them satisfy the constraints.
Right, and we have assumed full observability throughout this, and I would say that the algorithm has actually exploited full observability throughout the process. I do not think that, as it stands, it would work in partially observable environments. I think that POM-DP strategies would, which show information-seeking behaviors, would be very crucial in terms of constructing new symbols. And this is something that this current work doesn't support, because we assume that all the symbols are known a priori. So it's a big challenge, and I don't think that, as far as I know, there are very few answers to learning LTI formulas while also learning the specifications on the fly. I'm sorry, the propositions on the fly. And I know that So Nakul and others have done some work in translating language into LTI. But I think that was more of language grounding rather than grounding from trajectories. And I know that George has some work on symbol learning. And I think in the future, I'll be very excited to see if we can actually put these things together while learning temporal compositions along with the symbols themselves.
Cool. Yeah. So related to the learning question, one of the things we've been struggling with in our like LTL explorations with language is how to make it generalized. So like, if you like to sort of stick with the table setting example, like, you know, if you talk about the spoon, that corresponds to some symbol that is sort of hard coded in the state that, you know, corresponds to like object number 6 or something like that. And then you basically learn, like when we're doing our learning systems, you basically learn that like the word spoon corresponds to object number 6. And then you go to a different environment and there's a different spoon and it's object number 7 now. And you're kind of stuck. And we did this thing that I didn't really like, but it was something with like CopyNet and OpenStreetMap. I don't know if you saw that, where like you were like trying to like take the words, the spoon, and some kind of description of the object and do a thing. But like, I just wondered, like, have you thought about that kind of generalization, and how do we do that? Like, how do we know that object number 6 and object number 7 are both spoons and can correspond to the word spoons and stuff like that? Like lifted stuff.
Right. So in the current research, I haven't considered that. It is a question that keeps me awake at night in some sense. But I think what's important is, I think my intuition again, this is not coming out of any concrete work, but the intuition is that maybe atomic representation of objects may not be the right way to go about it, but really thinking about objects as a collection of attributes, which is an approach that you were describing, would be one step of the way towards that, where we are learning to associate tasks not with individual objects but with a collection over attributes, and that might help in transferability between objects. But again, this is speculative thinking, and I wouldn't say that I have any experiments to back that.
Yeah, we've talked about that a little bit, with like using attributes. And the thing that makes me nervous about it is that it seems like it's going back to like the wrong stuff that the GoFi people were doing, you know, where you have a bunch of, you know, like Shurdlu or something like that, right? Where you have a bunch of like pre-hard-coded attributes. And then I really come back, I don't know if that doesn't necessarily mean it's wrong, but it makes me nervous for that reason. And I wondered about also, like, I think the reason it makes me nervous is the connection to perception. I don't think that you want to know all the attributes all the time, because I think that would be intractable. And I definitely think you need to have a George symbol deep learned thing or something. You know, maybe like a LOMDP thing. I don't know if you saw that work, but like where you're like trying to figure out like how to go out and look for the attribute or something. But then I get confused about how that connects with LTL. We've been playing around with some stuff, but I just don't really know how to do it.
So I think that it's important to use LTL where it has strengths, which is the temporal compositions. Where LTL does not have its strengths is the definition of the propositions. So maybe LTL by itself is not the right specification language, but an automata-based approach that can leverage these temporal transitions is something that we want to take away from what we're considering in LTL. But as you said, like learning about attributes in an extendable fashion where we are not restricted to a set of attributes, but we can really learn what attributes to learn and the particular instantiations of those attributes. Like some sort of a first order representation of objects would be crucial going ahead. So I think your interpretation of this is something that resonates with me, which is why I'm very interested in collaborating in the future. And I think it would be speculation for me to say at this point whether that is the right answer or not. But I think that would be the approach that I would pursue as a first step.
Well, it's our job to make you speculate. That's and I also want to echo what other thesis people were saying. Like, this is really great work. I'm super excited about it, and it's really cool to see the growing consensus almost that LTL is the thing, and all the different cool things that we're doing with LTL, even though we don't think it's the end of everything, but like it's definitely a big important stepping stone along the way. So and we're super excited about you coming to Brown.
Thank you.
Thanks.
Thank you, Steffi. Michael, do you have a question?
Yeah, thanks. Thanks very much for including me, for inviting me, and for the great work and the great talk. I I couldn't hear a lot of it, sadly, because the audio quality was on my side partly. So I think in the echoey room that you're in is not ideal for this kind of thing. But like a lapel mic, that might have helped. But anyway, the point is, at this point, I had a question, if you wouldn't mind, talking about the observation that you made, which I think is a really exciting one, that a Bayesian approach can distinguish between two different hypotheses that both match the observations. And I was wondering if you could just kind of maybe briefly recap that argument, in case I missed it. And then if so, I think I have a follow-up question, because I think there are assumptions.
Absolutely.
That work.
So I think a good, let me just select the right slide for it, and I will project it. So I hope you can see my screen.
Yeah.
Right. So let's say that we have demonstrations that have shown the robot to place the fork, bowl, and the plate, and to place the dinner plate before the bowl. So that are some number of observations that satisfy this formula. But without an explicit data point which says that not placing the bowl is acceptable, or say not placing the plate is acceptable, we can't really eliminate these specifications as being incorrect. Or by saying that if you just do this and not this, that's incorrect, that is what's required to know with certainty that this is the right specification. So what a Bayesian approach allows us to do is to maintain a belief over the fact that this is the true specification versus this is the true specification, or another simplified specification being the correct one, without overcommitting to any one of them. And then the probability encodes the degree of the belief, which is what a lot of Bayesians like to interpret. So that's really the argument of adopting a Bayesian approach towards specification.
Right. No. I'm on board with the Bayesian approach. Okay. That's awesome. What I didn't get is the Bayesian update in this case. If I'm trying to reconstruct it in my head, and I'm finding that I need to depend on an explicit prior over examples or trajectories. And so that I don't see that in your story. And I was wondering, do you think it's not necessary? Because in my sense, it actually is necessary, because the probability of a disconfirming example is what drives the difference between the probabilities of those two hypotheses. And so you have to have some kind of assumption that, for example, there's some probability mass on examples that would.
That is correct. So I haven't addressed that explicitly, but implicitly, we consider that in a random setting, all possible executions are equally valid. So it's a uniform prior on that. So we never end up actually weighing that prior explicitly in the modeling. To adopt a more complete approach, we would actually require almost like a low-level representation of the robot, and that would induce a distribution over the states that the robot would accomplish. But I think as a domain-independent approximation, assuming equal probabilities over all trajectories works well. And we get the correct qualitative results in terms of confirming examples, giving us more probability over the correct or the specific hypothesis, and like the switch and the absence of forgetting to a limited extent. But I think like a complete Bayesian model would require us to do that much more explicitly.
that helps a lot. Thanks very much. Great job.
Thank you, Michael. Well, that was a great discussion. Thank you all so much for the questions and the back and forth, Ankit. I do want to open it up for Q&A for anyone else from the audience, but also want to note that the committee needs to finish deliberating by 3:30. So if there is a short, 1 or 2 questions we can get in the next 5 minutes, we'd love to do that. In the Zoom, please raise your blue hand if you have a question. And Ankit, if you see anyone with your hand raised where you are, please let us know.
Absolutely. I will call out the questions as I see them here.
Wonderful. I don't see any blue hands in the window. Okay.
Cheyenne? I see a hand from Cheyenne. Please unmute yourself and ask the question directly.
Hi, Ankit. Can you hear me? Hello, can you hear me? Sorry.
Yes, I can hear you.
Okay, awesome. Sorry. Firstly, yeah, thank you for the really wonderful talk. That was really awesome to see. And I think, when I first, I think I came across your Bayesian specification inference paper, I was really excited by it because it's like, for one, someone's like doing, inferring like, I think more structured sort of representations of what robots should be doing. I think maybe we'll get beyond, very unstructured reward, functions and actually solve the value alignment problem that way. But I guess the question I had, I was, it's really cool to see that you were drawing so much upon the work that we do in our lab, and with like the Bayesian concept learning and everything. And I was wondering, I was actually surprised to see that you managed to get inference working with WebPPL, because my immediate reaction is like, that's really slow. And I'm curious, in particular over these like really large intractable, like large hypothesis spaces that clearly got it working. And as you hope to expand, I think, to even more complex inference problems, how you see yourself solving, I think, the tractability issues with Bayesian inference, right? Like both in terms of the inference techniques and the kind of like modeling specific assumptions. Yeah.
Absolutely, that's a great question. And so one of the things is the project was really inspired from computational cognitive science project that I'd done for Josh's class. And I think if I were to do it again, I think the first thing I would do is to re-implement everything in Gen and not with people. I think modular inference and using different inference tactics for different types of distributions that we have used will be very key to scaling Bayesian inference up. And what really helped me scale up inference in web people was, I think, the combination of the correct problem size, correct abstraction of the hypothesis space, and then a problem where approximate inference worked well enough. So had I not had these 3 things together, I think we wouldn't have been able to complete the Bayesian inference demonstration as successfully as we did today. So I think web people was enough for that, but moving ahead, I really would want to use the more complex features that Gen provides. And I think it would be great to have a discussion with your lab and experts in Gen as to where Gen would be best suitable and what functions within Gen are best used for inference purposes.
Awesome, thanks. And yeah, I'd be very happy to talk about that stuff.
Yeah, thank you, Shane.
Wonderful. Thank you very much. Please, everybody, join me in clapping for Ankit for an excellent defense so far. And what I'll ask is, Ankit, can you put George, Hadass, Vaibhav, Nick, Michael, Steffi, and myself into a breakout room, and we'll discuss, and then we'll come back to you in a few minutes.
And we weren't able to do the acknowledgements live, but it is very important that I acknowledge a lot of people, because a lot of effort has gone into getting this PhD together beyond just what I have done. And this is being recorded later for those who are watching this, and this has been added to the video. So sorry about that, but please know that this is coming right from the bottom of my heart. So first of all, I really would like to thank my thesis committee for their extremely valuable inputs to this thesis. Julie has been a wonderful mentor throughout the year. She encouraged me to take on really challenging problems and come up with creative solutions for them, and to really not follow the crowd on research, and that was very valuable to me. Nick and Hadass have taught me to not shy away from the real complexities of the task and explicitly acknowledge what the limitations are while pushing forward with research. And this is not just in the domain of research. I think Hadassah makes leadership on making the robotics more community more inclusive have been exemplary through their leadership roles in various organizations, and they are really an inspiration for me. Um, George George has given me very strong technical advice and input at all the stages of my research, right from the formulation up to just a few weeks before the defense. And I'm very excited to be working with George in the future. Similarly, Stephanie, Michael, and Weber have been thesis readers and external evaluators while not being on the thesis committee, but their contribution to shaping the thesis as it is today has been incredibly powerful. Uh, all the way from lots of research discussions with Weber and a lot of life mentoring advice to a way of thinking about specifications that Michael told me about. And Stephanie has been a champion for partially observable domains, and that is something that I really want to incorporate into my research going forward. I would also like to thank the support staff at MIT Aeroastro, specifically Liz, who is the department administrator for our lab, who has been wonderful, be it running studies, procurements, reimbursements for conference travels. Liz has made our experience in the lab completely seamless. And special thanks to Beth for everything that has got to do with the department, be it the system handlers, be it being in compliance with all the regulations of the department, everything. I would also like to thank CSAIL for their wonderful venue and all the supporting resources that it has provided throughout this year. And thank you to Lockheed Martin and DCCRA for supporting different parts of my dissertation research. I really want to thank IRG, my lab, and these are 4 photos of IRG through various times. I think you will see yourself in some of them, and you'll see some of the previous members who you recognize in the rest of them. And IRG has been my home during my grad studies, and it's been a fantastic experience. I don't think I could have found a better group to do my PhD with. Uh, there have been many friends throughout this journey. Um, I have rediscovered old friendships, and all of you are like family to me. I've picked up new hobbies. I have explored lots of the US and outside. And thank you all for accepting me and being my family away from home. It has been special. Uh, Coming to the US was hard, and there's a lot of blessings that have sent me here, and there are a lot of I won't say expectations, but I would say aspirations for a lot of people back in India. And though they would have loved to be here, I think the current fire restrictions won't allow them to come here. And I know that every single one of them was watching the stream, uh, and this is after midnight at night. So thank you very much, and I feel blessed to have all of your support behind me for all of these years. Special thanks to Jeffrey. He has been a constant companion, a critic, and a sounding board for a lot of my ideas and a lot of work and personal let's just call them discussions throughout all of these years. So thank you very much for being there for me always. And last but not the least, I think my parents had seen the dream of me achieving the highest academic pinnacle of a PhD before I even knew what a PhD was. And without their sacrifices, without their training, and uh, without their support, none of this would have been possible. And I know that they wanted to be here so much, but they couldn't. And I see them attending the Zoom meeting from start to finish and somewhat beyond the finish as well. So a big thank you to my parents. And that's really it. So hope you enjoyed my presentation, and I'm very sorry for not being able to go over the acknowledgements during the actual live presentation.